to question 6, and obviously this is the same motto as question 5, but now it is cumulatively compounded. Okay, so if the motto is connected cumulatively compounded with R adjusted 175 ohms, what is the no load speed of this motto? Okay, obviously when we're looking at this question, that we know that will be the effect of the series what you call winding to the armature circuit. Okay, so you will be adding up more magnetomotive forces or more flux inside the system lah. Okay, so or inside the machine. Okay, so therefore, first of all, when we are looking at the no load speed, we know that there is no current flow actually inside the armature circuit, because the current EA at that point will be equals to VT. Okay, so because if we look at the how the motor actually operates, right? If you turn off the if you start the machine, the EA is originally at 0 volts, okay, and it increases until it is equals to VT at no load speed. Okay, so when that happens, basically when the EA equals to VT, there is no difference in potential, then obviously the armature current will not flow inside the armature circuit. Okay, so when we're talking about no load speed, we're talking about IA is actually equals to 0. Okay, so therefore at no load condition, EA is simply equals to VT. So in this case, VT is actually equals to 240 volts. Right. So to look at, so we are given the magnetization curve. So to actually find out how much internal generated voltage that we get at certain speed, right? So therefore, from the magnetization curve, we know that the independent variable is actually at the x-axis, which is the shunt field current. So if we want to read anything from the graph, we need to find out what is actually the field current that we have right now, so that we can read something from the graph. Okay, so IF, or the field current, is actually equals to VT over RF plus R adjusted, okay, which is equals to 240 divided by RF is 75, R adjusted is adjusted at 175, so we have 240 over 250, okay, which is equals to 0.96 ampere, or close to 1 ampere lah. Okay, so from this figure, okay, so close to 1 ampere, we can actually see that this field current will produce an internal generated voltage of about 240 plus. Let's approximate this to like 241. Okay, so you will get EA equals to 241 volts if the motor is actually running at 1800 RPM. Okay, remember, magnetization curve is always plotted at single speed. Okay, so different speed will give you different value of EA. Even though the shape of the curve is the same, you will have different reading at EA at a different speed. Okay, so therefore, in this case, the reference is actually, if you have 0.96 ampere of field current fed into the machine, and if the machine is running at 1800 RPM, you will get 241 volts. But at this case, your EA is actually 240, right? Because at no load, EA is equal to VT. So you can actually use this comparison by following the ratio that we actually talk about in the class, in the theoretical class, in which EA at one condition, okay, is equals to K prime phi 1 and 1, and EA at the second condition is K prime phi 2 and 2. Okay, since we are actually looking at the same machine, the K is the same, okay, and we are running at the same field current. Okay, so this 241 volts, 1800 RPM is read at IF equals to 0.96. Okay, and 240 volts also you get when your IF is also 0.96. So your flux content in the machine is the same. Okay, so if we rearrange, we know that EA1 over N1 is K prime phi 1 and EA2 over N2 is K prime phi 2. Since both of these term is the same, so we can simply equate this equation together. Okay, that's why we get this equation. So this is just a reminder of what actually happens with this equation. Sorry. Okay, so the first reference that we can get is 241 over 1800 RPM. Okay, and the EA that we actually get at no load is 240 volts. Okay, and the speed is what we want to find. Okay, so the speed is actually 1800 divided by 241 times 240. So it's actually 1792 RPM when it is at no load. Okay, all right. The question B, okay, what will be the full load? Okay, so what happened at full load? At full load, I line or line current will be actually equal to the rated current lah, which is 110 ampere. Okay, so at that point, IF is actually IF is actually I line minus, IA is actually IL minus IF. Okay, since IF right now is 0.96 ampere, and 110 minus 0.96 will get like 109 ampere. Okay, yeah, point something, but you can approximate that 0.109 ampere. Then obviously the internal generated voltage is not equals to VT anymore because we have the term IA. Remember, EA is VT minus IARA. With no load, IA is 0, right? So this whole term got cancelled straight away. But now since IA we have value, so we have to calculate this. So 240 minus 109 times RA is 0.19 ohm. Oh, sorry. So since we are actually connecting it as cumulatively compounded, we have not just simply RA but also RS together in the circuit. So RA is 0.19 and RS is 0.02. Okay. Alright. So this will be the final equation. So 240 minus 109 times 0.19 plus 0.02, and this will give you 217.11 volts. Okay, so this is EA when it is at full load. Okay, so we have actually the reference already previously, because right now IF is still 0.96, so therefore we can use the same reference that we have before, which is 241 and 1800 RPM. Okay, so the speed at full load is actually, we first write down the reference, okay, and the speed the speed that we actually wanted to know. So the reference is 241 at 1800 RPM, and EA2 that you get is 217.11 volts. Okay, and the speed that you want to know is N2. Okay, so I will calculate 1800 RPM divided by 241 times 217.11 will give you the full load speed at 1622 RPM. Okay, so this is obviously expected lah, okay, because no load will always be higher than a full load speed. So sometimes when you want to check whether your calculation is correct or wrong, at least look at the theory and find out where your answers lie. Okay, so for example, if you have a full load speed that are much higher than a no load speed, so you should check your question. Either there is only two possibilities: either you calculate it wrong, or the question has armature reaction. That is the only explanation. Okay, so that's why you need to also concurrently check with your theories to make sure your calculation is correct. Okay, so the third part is what will be the full load speed of the motor if R adjusted is increased to 250 ohms. Okay, so we just talked about that just now with shunt circuit. Okay, and we know that when we change R adjusted, then obviously the effect, the field current will be different, right? So the field current now, instead of 0.96, it will be 240 divided by 75 plus 250. Okay, so 240 divided by 75 plus 250. Oops, sorry. 250 will give you 0.739 ampere, or 738 ampere. Okay, or 74 ampere lah senang. Okay, so IF is 0.74 ampere. Okay, so now IF, instead of 0.96 ampere, becomes 0.74 ampere. So in this case, okay, EA, in your case, originally actually checked at 0.96, right? So right now we cannot use that anymore. So we can only check what happens at IF equal to 0.74. So if we take a look at this point here, right? So 0.74 is somewhere there. Okay. So we're looking at about 210 volts, right? So EA is actually 210 volts for this if the speed is running at 1800 rpm. Okay, so this is if the field current is 0.74. Okay, now okay, so now what is actually the full load speed? And we know that the what you call, from the previous part that we calculated the full load EA, okay, which is 217.11. So at full load, basically EA is still maintained at 217.11 volts. Okay, so therefore we are trying to find out how much the speed of this machine when there are differences in flux inside the machine, okay, right now, right? So we know from the equation that EA is K prime phi 1 N1, okay, and EA2 is K prime phi 2 N2, okay. So so basically we know that the reference for this point is actually, if we're looking at the part B, okay, so that part B is we have internal generated voltage as 217.11, right? 217.11 with the speed of 1622 rpm. Okay, and with the same machine, so K prime is the same, but the flux is different. Okay, so EA2 is basically the values that we consider we are having right now. So we are also having 217.11 volts for EA2 because it's still running at full load, and the flux basically is different because we have different field current right now, and of course we want to know the speed. Okay, so therefore since EA is the same, then we know that N2 is simply phi 1 over phi 2 times N N2 is phi 1, yeah, over phi 2 times N1, and this is we can actually look at the ratio between EA1 and EA2 or EA when the field current is 0.96 and EA when the field current is 0.74, and times with the first what you call speed, which is 16 to 2 or sorry 1800 rpm. Okay, so basically if we take a look at this, we can see that EA when IF is 0.16 is actually EA at 0.16 is 241 volts, right? So 241 volts, and EA at 0.74 is 210. Okay, so times be 1800 rpm. Okay, so this will give you different values for your speed there. So 241 divided by 210 times 1800 rpm is 2065 rpm. Okay, so we can see that when we increase the R adjusted, obviously the speed goes up. Okay, so the full load speed, because of a different what you call, because of the different field resistance that are applied, we have a different increasing field resistance, we will have an increasing speed in a full load. All right, so I hope that clears out the question.